Hello, today we're going to be covering the strong nuclear force and nuclear stability. We'll start by going over what the strong nuclear force is, and then discussing what happens when we have an imbalance of protons and neutrons in the nucleus. Finally, we're going to be calculating some of the products of alpha and beta decay. Let's start with the basics. The nucleus is made up of two particles, the proton and the neutron. However, there's an issue here that you might not have identified in the past. Positive charges repel. Therefore, we might expect the positive charges from the protons in the nucleus cause it to break apart. This, of course, doesn't happen. The reason for this is we have another attractive force keeping all of the nucleons together. We call this attractive force the strong nuclear force. One important feature of the strong nuclear force is that it acts between all of the nucleons inside the nucleus, including the neutrons. This is different from the electrostatic repulsion, which only acts between the protons. Another important feature of the strong nuclear force is that it only acts at very small distances, typically over only a few femtometers. A femtometer is equivalent to 1 times 10 to the minus 15 meters, which is approximately the scale of the nucleus, hence why we only meet this force inside the nucleus. Here's a graph showing how the strong nuclear force's magnitude varies with distance. As we can see, at very, very short distances, less than half a femtometer, the strong nuclear force is actually a repulsive force. However, as we go out, it then becomes an attractive force, peaking at around 1 femtometer. This roughly equates to the mean distance between the nucleons. As we keep going out, however, the magnitude of the strong nuclear force decreases. By the time we get to about 3 femtometers, the electrostatic force is much greater in magnitude than the strong nuclear force. Hence, at this distance, we can say that the strong nuclear force is negligibly small. Pause the video now and try these exam-style questions to test your knowledge of what we've discussed so far. I would advise to use a pen and paper to write down some answers to these questions. My answers will follow shortly. The force that keeps the nucleons together is, of course, the strong nuclear force. A femtometer in standard form is 10 to the power of negative 15 meters. The strong nuclear force is repulsive and then attractive. At short range, it's repulsive, that's less than half a femtometer, and at greater than half a femtometer, it's attractive. However, at longer than 3 femtometers, it becomes small or negligible compared to the electrostatic force. And finally, the reason we need the strong nuclear force is to keep the nucleus together. The protons have positive charge, which means they must be repelling each other. There must be therefore another force which is responsible for holding everything together. Okay, one important implication of the properties of the strong nuclear force is that an imbalance of protons and neutrons will cause an atom to become unstable. The strong nuclear force only acts over very short distances, whereas the electrostatic repulsion can act over much greater distances. This means that some of our larger atoms tend to be unstable. Those are things like uranium, neptunium. If you have an atom with a large imbalance of protons and neutrons, they will tend to be unstable. Nuclei will return to a more stable state by emitting radiation. For example, if you have atoms with an excess of protons, they'll tend to decay through the emission of an alpha particle. Similarly, atoms with an excess of neutrons will tend to decay through the emission of a beta particle. Let's look again at alpha decay. Alpha decay is where we give off an alpha particle, that is, 2 protons and 2 neutrons. Let's take an example. Uranium-238 decays to thorium-234 through the emission of an alpha particle. This alpha particle is often notated as He42, as it's exactly equivalent to a helium nucleus. The parent, we say, has lost 4 mass to the daughter because 2 protons and 2 neutrons have been emitted in the alpha particle. We can write an equation for this using nuclear notation. What we say is that a parent nucleus X has a nucleon number A and a proton number Z. After its decay to a daughter nucleus through alpha emission, it will have a nucleon number A-4 and a proton number Z-2. We also emit the alpha particle, notated as He42. We can do something similar for beta decay. In beta decay, a neutron in the parent nucleus decays into a proton in the daughter nucleus. This is accompanied by the emission of a beta particle, which is simply a fast-moving electron. We can also write down an equation for this. Again, very simply, the proton number in the daughter nucleus increases by 1, whereas the overall nucleon number remains unchanged. Here's another chance for you to have a go at some questions yourselves. Use the general form of the equation for alpha and beta decay to fill in the missing proton and nucleon numbers for each of these nuclei. You can also try the extension at the bottom, which is particularly challenging. Pause the video now. Here are the answers for that set of questions. The answer to the extension was 6 separate decays.